Welcome to a deep dive into the revolutionary NOVA-Σ Field Propulsion System. In this video, we'll explore the technical foundation, mathematical models, and stunning 4K diagrams that define a new era of mobility. Unlike traditional propulsion, NOVA-Σ operates without exhaust or aerodynamic lift, relying instead on engineered field gradients and inertial modulation. This chapter sets the stage for understanding how field-driven motion is achieved, the core physical principles at play, and the advanced materials that make this technology possible. Let's begin by outlining the key properties and the unique approach that sets NOVA-Σ apart from anything before it. NOVA-Σ field propulsion is a clean-sheet, post-reaction mass mobility architecture. Instead of pushing against air or expelling mass, this system produces motion by manipulating field gradients and modulating inertia. The result is a propulsion method that works in any environment: air, water, vacuum, or plasma. The system is closed-loop, meaning it manages its own field momentum internally, and it achieves continuous stability through tensor continuity. This overview introduces the core idea: motion as an emergent property of field geometry, not mechanical force. The heart of NOVA-Σ propulsion is the concept of creating a spatial gradient in effective inertia, coupled to an energetic field potential. The craft generates its own gradient and moves along it. This means that motion is not forced by pushing against something, but rather emerges from the geometry of the fields the craft creates. The vehicle's movement is a direct result of how these fields are shaped and managed, making the process fundamentally different from conventional propulsion. To understand NOVA-Σ, it's essential to know the key variables and fields involved. The effective inertial tensor field, energetic field potential, field gradient vector, velocity components, and background metric all play crucial roles. These variables interact to define how the craft manipulates its own inertia and field environment, enabling precise control over motion and stability. Each parameter is mathematically modeled to ensure predictable and controllable behavior. Effective inertial tensor is a mathematical construct that allows the craft to selectively accelerate without needing to expel mass. By controlling the internal field states, the system can modulate inertia in specific directions. This directional inertia is what enables the craft to move efficiently and responsively, adapting to different operational needs without relying on traditional thrust. Energetic potential field is another core element. By creating non-zero gradients in this field, the craft can produce translation. Essentially, it moves itself by shaping the potential landscape around it. The equations governing this process tie directly to the visual representation of field lines and gradients, making it possible to both predict and visualize the craft's behavior in real time. Like conventional vehicles, acceleration in NOVA-Σ arises from time-varying inertia and field gradients, not from force expulsion. The governing equation links the rate of change of the inertial tensor and velocity to the gradient of the energetic potential. This approach allows for smooth, controlled motion without the need for exhaust or moving parts, fundamentally changing how we think about propulsion. NOVA-Σ system is built from 4 integrated layers: the sigma core inertial lattice engine, gamma engine gradient field generator, omega sheath environmental decoupling field, and lambda matrix control and stability intelligence. Each layer has a distinct function, working together to create a robust, stable, and highly controllable propulsion system. This architecture is visualized in detailed 4K diagrams, showing how each component contributes to overall performance. Key innovation in NOVA-Σ is the use of advanced materials, starting with the Tensor-Active Meta-Lattice (TAML). This structural lattice is phone-unlocked, enabling real-time modulation of the inertial tensor. With a high stiffness-to-mass ratio and lossless vibrational routing, TAML allows the craft to shape its inertia dynamically, supporting both efficiency and stability in all operational modes. Field-persistent Electret-Ferroelectric hybrid, FPEH, is another breakthrough material. It maintains stable polarization even under extreme fields, defining the internal field topology and anchoring gradient vectors. This material ensures long-term charge coherence, which is critical for maintaining the integrity of the propulsion system's internal fields during high-energy maneuvers. Polaritonic boundary skin, PBS, forms the craft's multilayer surface, supporting strong light-matter coupling. This skin nullifies drag and pressure, provides electromagnetic and thermal shielding, and ensures field line continuity at the hull boundary. By integrating these advanced materials, NOVA-Σ achieves both protection and performance, even in the harshest environments. Bring these concepts to life. NOVA-Σ is documented with ultra-realistic 4K technical diagrams. These visuals show field lines, tensor grids, and energy flows in cinematic scientific clarity. Each figure overlays mathematical equations and vector annotations, providing both a visual and analytical understanding of the system's operation. Let's explore each figure in detail, starting with the full Cutaway field overlay. Figure 1.1 presents a cutaway diagram of the NOVA-Σ craft, revealing its 4 concentric internal layers. Glowing curved field lines bend around the hull, color mapped from blue to red to indicate energetic potential. Vector arrows labeled -5 point forward, while a transparent tensor grid inside the core displays eigenvector arrows and magnitude annotations. Mathematical equations float near each subsystem, tying the visuals directly to the underlying physics. Figure 1.2 shows the craft hovering motionless above a flat reference plane. The hull is transparent, revealing internal systems. Symmetric vertical field lines, glowing soft cyan, extend above and below the craft. A vertical gradient arrow labeled phi equals is displayed, with no horizontal vectors present. Inside, a uniform inertial tensor grid indicates identical eigenvector lengths in all directions, emphasizing perfect stability in hover mode. Figure 1.3, the craft is depicted in forward motion. Dense, compressed field lines appear ahead of the craft, while elongated lines trail behind. Forward-pointing vector arrows labeled -phi-x highlight the direction of movement. Inside, the inertial tensor grid is anisotropic. Forward eigenvectors are shortened, while lateral and vertical ones are longer. This configuration enables efficient forward acceleration with minimal resistance. Figure 1.4 illustrates a high-G maneuver, with the craft angled sharply. Compressed inertial tensor zones are visible on one side, while expanded zones appear on the opposite. Internal load redistribution, arrows flow toward reinforced regions, and external field lines remain smooth and continuous, wrapping the hull without turbulence. This demonstrates the craft's ability to maintain stability and control even under extreme acceleration. Maintaining stability is crucial for NOVA-Σ operation. The system enforces conditions to prevent inertial or field discontinuities, such as ensuring the divergence of the inertial tensor is zero and limiting the time rate of change of the field gradient. These mathematical constraints guarantee that the craft remains dynamically stable even during rapid maneuvers or environmental changes. One of the most remarkable features of NOVA-Σ is its independence from the surrounding environment. Because it does not exchange momentum with air, water, or plasma, the same dynamics apply in any medium. The environment becomes merely a boundary condition, not a requirement for operation. This opens up possibilities for operation in space, underwater, or even in extreme atmospheric conditions. Summarize Chapter 1 establishes NOVA-Σ as a mathematically defined, field-driven propulsion system. The chapter introduces the physical model, governing equations, and advanced materials, all visualized through detailed 4K diagrams. This foundation sets the stage for deeper exploration into control logic, multi-craft interaction, and advanced mission profiles in subsequent chapters. This version of the dossier represents a hard reset, free from previous naming conventions or speculative elements. NOVA-Σ now stands as a clearly defined propulsion identity, with explicit 4K diagrams and equations directly tied to the physics. Materials are upgraded and mapped to their functions, and the document reads like a true defense or aerospace technical dossier, ready for use in renders, patents, or program books. Support technical visualization. Exact 4K image prompts have been generated for each figure. These prompts are designed for high-end image generators, ensuring realistic, cinematic scientific diagrams that accurately represent field lines, equations, and overlays. Each prompt is precise and optimized for clarity, making them ideal for technical documentation and educational content. Prompt for Figure 1.1 calls for an ultra-realistic 4K cutaway diagram of a futuristic lenticular field craft. The image should show 4 concentric internal layers, glowing curved field lines, and vector arrows labeled -phi. Inside the core, a transparent tensor grid with eigenvector arrows and magnitude annotations is displayed. Faint mathematical equations float near each subsystem, all rendered with photorealistic lighting and sharp edges. Figure 1.2, the prompt specifies a craft hovering above a flat plane with a transparent hull and internal systems visible. Symmetric vertical field lines, glowing cyan, extend above and below. A vertical gradient arrow is labeled, and a uniform inertial tensor grid is shown inside. The style is clean and precise, with realistic lighting and no motion blur, emphasizing the craft's perfect stability in hover mode. Prompt for Figure 1.3 describes a craft in forward motion, with dense, compressed field lines ahead and elongated lines trailing behind. Forward-pointing vector arrows and an anisotropic inertial tensor grid are depicted, with forward eigenvectors shortened. The image should have sharp vector lines, restrained glow, and a high-fidelity aerospace simulation look, all rendered in 4K resolution. Figure 1.4's prompt features a craft executing a high-G maneuver, angled sharply with internal systems visible. Compressed inertial tensor zones and expanded regions are shown as a distorted tensor grid, with load redistribution arrows. External field lines wrap smoothly around the hull, indicating environmental decoupling. The style is technical, with realistic lighting and ultra-detailed 4K realism. Moving beyond single craft operation, the NOVA-Σ system is documented in a formal technical report covering Figures 1.5 through 1.8. These figures extend the framework to multi-craft field interaction, cooperative stability, tensor field envelope control, and degrees of freedom decoupling. The report establishes NOVA-Σ as a scalable field-based mobility architecture capable of coordinated motion and formation flight. Go 1.5 depicts 3 NOVA-Σ FIELDCRAFT in cooperative formation, each surrounded by its own structured gradient field. Together, they contribute to a shared coherent field network. The system transitions from isolated gradients to superposed field topology, enabling mutual stabilization, shared inertial biasing, and coordinated acceleration. The formation behaves as a distributed propulsion organism, not just a group of discrete vehicles. Multi-craft operation, each vehicle maintains its own localized scalar potential, but the group forms a superposed field. Control matrices enforce phase-lock coherence, resulting in mutual stabilization and coordinated acceleration. Intercraft spacing is maintained by gradient equilibrium surfaces, and the formation can perform swarm flight, load sharing, and formation-level thrust amplification without collision risk. Ability to operate in coordinated formations enables advanced capabilities such as swarm flight, redundant stability during high-energy maneuvers, and distributed load sharing. The system's architecture allows for formation-level thrust amplification, making NOVA-Σ ideal for complex missions requiring multiple craft to work together seamlessly. Go 1.6 illustrates the stability envelope surrounding a single craft, visualized as a closed tensor field shell. This envelope defines the region where disturbances decay rather than amplify, ensuring dynamic stability. External disturbances are absorbed by tensor redistribution, and internal oscillations are damped before reaching instability thresholds. The craft remains stable without aerodynamic surfaces. Stability envelope is mathematically defined by the dominant eigenvalue of the inertial tensor and the Laplacian of the field potential. If the eigenvalue is negative, perturbations decay, ensuring stability. This allows the craft to hover in turbulence, perform high-G maneuvers, and operate stably in plasma, vacuum, or dense fluids, all without relying on traditional aerodynamic surfaces. The robust stability envelope, NOVA-Σ can sustain hover in turbulent conditions and execute high-G maneuvers without loss of control. The system's ability to damp internal oscillations and absorb external disturbances means it can operate reliably in a wide range of environments, from atmospheric turbulence to the vacuum of space. Go 1.7 demonstrates intentional anisotropy in the inertial tensor, allowing the craft to bias performance in specific directions. By reducing inertia along the acceleration axis and increasing it orthogonally, the craft can achieve rapid directional changes and instant acceleration without structural stress. This is the mechanism behind the non-Newtonian motion profiles observed in advanced fieldcraft. Core equation for directional tensor reshaping involves transitioning the inertial tensor to a new state where the changes along each axis are different. This controlled asymmetry lets the craft reshape its resistance to motion, enabling right-angle turns, sudden stops, and instant acceleration, all without imposing inertial lag on occupants or internal systems. Reshaping its inertial tensor, NOVA-Σ can perform maneuvers that would be impossible for conventional vehicles. This includes rapid directional changes, right-angle turns, and sudden stops, all executed without structural stress or inertial lag. The craft's internal systems and occupants remain isolated from the forces typically associated with such maneuvers. Go 1.8 visualizes the decoupling of translation and rotation, allowing the craft to control all 6 degrees of freedom independently. Linear acceleration is not coupled to angular momentum, and rotation does not induce translational drift. This enables perfect rotational control during linear acceleration and complete isolation from inertial stress for both occupants and payloads. Control law for degrees of freedom decoupling ensures that linear acceleration and rotation are managed separately. This means the craft can spin without displacement, translate without rotation, and perform precision docking or extreme maneuvers in confined environments. No centrifugal forces are transmitted internally, preserving comfort and safety. With full 6 degrees of freedom decoupling, NOVA-Σ can perform spin without displacement, translation without rotation, and precision maneuvers in tight or hostile environments. This capability is essential for advanced mission profiles, including docking, formation flying, and operations in unpredictable or hazardous conditions. GOS 1.5 through 1.8 collectively demonstrate that NOVA-Σ is more than just a propulsion system. It scales from single craft to coordinated formations, maintains stability through tensor field envelopes, achieves non-Newtonian maneuverability via inertial shaping, and fully decouples classical degrees of freedom. This establishes NOVA-Σ as a field-governed mobility platform, free from the constraints of reaction mass or conventional propulsion limits. Technical diagrams and figure prompts are designed for poster-sized 4K generation, making them suitable for both educational and professional use. Each visual is accompanied by chapter details and precise annotations, ensuring clarity and accessibility for audiences ranging from engineers to enthusiasts. NOVA-Sigma's architecture is ready to drive actual 4K renders, be expanded into classified program books, and serve as a reference for patents, videos, and posters. The system's scalability and adaptability make it a prime candidate for future aerospace, defense, and scientific applications, pushing the boundaries of what's possible in field-driven mobility. The foundational chapter complete, the next steps include generating additional figures for multi-craft interaction and stability envelopes, converting diagrams into post-ready captions, and creating animated motion phase prompts. These efforts will further align the technical visuals with educational and professional video segments, enhancing understanding and engagement. Looking ahead, Chapter 2 will delve into control theory, eigenvalue stability, and failure modes. This next section will formalize the logic behind multi-craft coordination, stability under extreme conditions, and the mechanisms that prevent system failure. Stay tuned as we continue to build on the mathematical and visual foundation established in Chapter 1. Summary: NOVA-Sigma represents a paradigm shift in propulsion technology. By leveraging field gradients, tensor modulation, and advanced materials, it achieves motion and stability in ways previously thought impossible. The detailed 4K diagrams and technical models provide a comprehensive reference for engineers, researchers, and enthusiasts alike, marking the beginning of a new chapter in field-driven mobility. Thank you for joining this exploration of the NOVA-Sigma Field Propulsion System. As we move forward, the combination of mathematical rigor, advanced materials, and cinematic technical visuals will continue to illuminate the path toward the next generation of mobility. Stay tuned for more chapters, figures, and in-depth technical analysis as we unlock the full potential of field-driven propulsion.